Recall that just now we say that the expected values will be put into matrix B. So what we can do is to obtain the expectation is to second this for matrix and just go down to B, press enter, and press enter again. You will see the values in decimal places. This is not very accurate. So we can do math. All right, go to fraction, that's number 1, press enter. And now press enter again. And now I get all my value in terms of fractions. So I can just write up. So the first one is 832 over 25 and so on. Now we will calculate the chi-square statistics for this experiment. Or here, this is the table of the observed value. Here is the table of my completed expected values. So what we need to do is to do this particular process. So the first thing is that the observed value, the first one is red and female, so it's 43 minus the expectation of female and red, 832 over 25, and observe that I keep the fractions so that I get as accurate as possible the answer that I'm going to obtain. So that's the first one, plus the second one is female and blue, so it's 26 over here, minus this expectation, 923 over 25, everything square, over 923 over 25. And I will repeat this process until I get to the last one. Here I've written all the expansions and calculate the value to be around 17.2 to 3 significant figures. Then in step 3, it looks at the degree of freedom. And basically this theoretical value, right, is this. Well, I get 17.2. Well, is this a small number or a big number? Because if all the observed value are very close to expectation, in fact, if all the observed value is the expected values, then the numerators will be all going to be zeros. And this chi-square statistics in this sense will be actually 0. So the smaller, the closer the value to 0, that is the observed value as closer to expectation, then what we know then is the observed value is very close to being one of the independent. That is, the two events are actually independent. So the question is then 17.2, is this a small value or a large value? If it's a small value, then we can say the data support the null hypothesis that these things are independent, color and gender independent. If this is a large number, then we say gender and color are not independent. So to answer this question, whether this is a small or big, then we need to have a benchmark for what values to be considered small. This benchmark is called the critical value. The critical value is affected by two things. One is the degree of freedom. Now, degree of freedom is calculated as the number of rows minus 1 times the number of columns minus 1. So in our case, we have 2 rows. So we have, in this case, 2 minus 1 times columns. We have 4 columns, so 4 minus 1. So the answer to this is 1 times 3, or just 3. So what it does say is that the degree, so the critical value here, whether the number is big or small, really depends on how many data that you're going to have, right? If you have a lot of data, then the critical value tends to be larger. If it is less data, then it's going to be smaller, for example. And the other thing is that the critical value also depended on the risk that you are willing to take. And this is called the significant level. For example, very often you hear that we use this 5% significant level, right, in the test. What it means is that we are willing to accept the probability 0.05, or in colloquially we say 5% chance that we rejected the null hypothesis, that is of independence, when it is actually true. In another word, is that although the null hypothesis is true, that is, although the two events are actually independent, we incorrectly rejected the null hypothesis based on the observation that we have from the data. And that risk is 5%. That's what I mean by 5% significant levels. And in statistics, this is often used as, often use 5%, 10%, or 1%, for example, right? Often it's 5%. In recent years, this significant levels is used less often because of the capacity of the calculator and GDC to calculate the p-value. So instead of calculating the significant values, people just report the p-values.